Hello everyone. In today's session, we are going to discuss the vector division. We know that a vector is a quantity with both magnitude and direction, e.g. acceleration, velocity, and force. And we also know that we have also a scalar, which is a quantity with magnitude only, e.g. mass, temperature, and time. And then we can represent the vector. We have said it has both directions. So let me take my highlighter here. I can have this pen. And here we can say that a vector will be represented as, maybe we can have that line. So here we have A, and here we have B. And there we have B. So the direction maybe moves like that. So that is how we can represent a vector. Remember, if you have to state this, we can say that this is vector A, B with this direction at the top there. If, for example, we were given that AB is equals to A, we could also represent it as that with that symbol below it. And also, we can say that the magnitude, we can represent the magnitude or the length of this line as A, B, and then we have that. That is how we can represent the magnitude of that line. And remember, we can also say that A is the initial point and B is the terminal point. That is how we can represent the vectors. So we have the equivalent vectors. So we can say that two or more vectors are said to be equivalent if they have one, equal magnitude, two, the same direction. So maybe, for example, if I have this line that way, and I can call this one to be V, and then I have another line here like that. This one is W. So I can say that V is equals to W. V is equals to W, and that one is an example of an equivalent vector. So you can see they have the same magnitude, that's the same length, and also they are in the same direction. But still, I can have it in a different direction, where maybe I have this one moving in this direction like that. Sorry. And then I have this one downwards like that. And now, assuming that these ones are the same, this one may be U and this one may be to be T, we can say that my U is equivalent to negative T, because you can see that the T moves in opposite direction to that. Remember only that mine is not drawn to the accuracy, but they are supposed to be the same. Maybe, for example, if I have maybe this kind of a triangle, if I add this kind of a triangle like that, sorry, and here I have point B, here is C, and here maybe is A. So this one is maybe I have this one being A, and this one being B. So remember, I can express line AB in form of, maybe I have AC, maybe added to B, maybe added to CB, that way. So meaning that I can have this one as A and then plus B. So that is how I can express that line. That is A plus B, A plus B. So then remember also we can have a zero vector. And a zero vector, we normally say that if we consider a displacement from A to B and then B to A, maybe, for example, I have this line being my initial point being A and my terminal point being B. So if there is a displacement from A to B and then B back to that, we can give it as maybe AB, then plus B, A, and this one we can say is equals to 0. Why are we saying it is equals to 0? Because when we change the direction, a vector having a given direction, we have to express this in negative. Maybe this one was positive a, and then this one is plus minus negative a, and this one will give us a 0. So that is how we can express a 0 vector. And then we have multiplication of the vectors by the scalar. Remember we said that a scalar have a magnitude only. So in this scenario, we can have line maybe AB is equals to maybe BC, and then BC maybe is equals to CD, and all of them we can say that they're equivalent to M. So in these, we can express, if you're told to give line AD, we can say line AD is equals to maybe the first displacement of AB, which is A, then plus the second displacement of BC, which is A, maybe plus the other displacement of CD, which is A, and at the end we get this one is 3A. So you can see it's like if we are multiplying a scalar of 3 with the vector. We can still have it in the negative direction, whereby maybe if we want now to get DA, it will be the other way opposite, that is negative A for the first DC, and then we had to negative BC, CB, which is also negative A, and then we had to negative BA, which is also A. And if you add all this, that is a negative, give us negative 3A. So that is a negative scalar. And then if we have a 0, if we multiply vector A, maybe we multiply by a 0, or maybe if we have it being, we start with a 0 multiplied by a vector, this one will always give you a 0. So that is how we can say that is a 0. Then remember also we can have multiply a vector by a scalar. So if I have a scalar like K, A, and also this one is a positive, positive scalar, and then remember I can also add in an opposite direction, where maybe I have a negative maybe KA, negative KA. So remember this one is in opposite direction, that way. So that is how you can multiply the vector by a scalar. And then we have also the magnitude. And meaning we have said that we can express the magnitude. Maybe for example I have line A, B, that way. So, and maybe I can assign it the values of maybe 2, 3, and then here I have 8, 7, that way. So this is 3. So meaning that if I want to get the range of that line, I must say that A, B magnitude will be given by, will be equivalent to the square root of x squared plus y squared. And for me to get this, the length of AB, remember if I'm referencing this one to point O here, I'll say this one is the same as B, then I subtract A, B, I subtract A, meaning that in this case I will have 8, maybe I'll have 8, 7, then minus 2, 3, and in this case I'll get my A, B equivalent to 6, and 4, that way. So now the magnitude of AB will be equivalent to the square root of 6 squared then plus 4 squared, which is equals to maybe the square root of 36 plus 20 and the 4, 36 plus 24. So this one is the same as what? If I add the 2, I'll get this one as 60. The square root of 60. I'll get that one as the square root of 60. I can look for the two factors that I can multiply, maybe to get 60 and at the same time add them. And if I have maybe 4 multiplied by 15, this one will give me 215. So also you can express it in terms of that, or you can use your calculator and get it with the correct value in decimal places. So the next value that I need to get, I have the position vector, and we normally say that a position vector is the image of the origin and the translation, and we also say that it is fixed or tied to the origin. So a position vector describes the spatial position. So maybe, for example, if I had my Cartesian plane as that, so always this one is the origin 0, 0, and if I have a point here, maybe I have a triangle like that there, I'll always reference this point A, maybe B and C. I'll always reference it from the origin here, which is maybe, for example, this one, which is O A, and then O B and maybe O C. So always to get these, I'll have to reference it such that, so meaning that the point O, remember this one is 0, 0, and maybe if I had here the point A to be 3, 2, if I was to get this OA, referencing that, remember I will say 3, 2, then this one I subtract 0, 0, that way, and of course I'm going to remain with the same point 3, 2. So meaning that the origin doesn't have any effect on that when I'm considering the Cartesian plane. Then we have the translation vector. Translation vector, we say that this one will move every point of an object by the same amount in a given vector direction. That is addition of a constant vector to every point. Maybe, for example, I have the example there where we have a point -4 plus that, -4, and that are the vertices of a quadrant. Under the translation of that, find the image. And in that case, for me to get the image with the reference, maybe, for example, the first image is, maybe I want to get O with the origin of that. O A will always be given by A plus A, that is AO plus the translation. So meaning that if I want to get the first point here, this one is the same as, maybe we have this one is the same as -4, 4, then this one plus we have here, which is 5, and then -3, because that's our translation. So to get our A prime, which is the image, this one is the same as, if I take -4 plus that, I get 1. I get that one to be 1, and then 4 minus that, also this one is 1. So 0.11 becomes the image of point that. Then to go to the same O, B prime, here I'll have B added plus the translation, because we have said translation is addition, is a constant vector to every point, which we can say this one is the same as point B has negative 2, 3, then this one is added to 5, then negative 3, 5, then negative 3, that way. And if I add this, the first one, remember, if I have to add these, I'll get this one being negative 2 plus 5, this one is a 3 positive, and then 3 plus minus 3, this one is a 0. So my point B here, I can say it is equivalent to 3, then 0. Remember, that one is the one that I'm going to plot now to the Cartesian plane. And then I have OC prime. This one is the same as I get the point of C, which is C, then added to the translation. So, and in this case, I'm going to have negative form, negative 4, then 1, and then this one I add to my translation, which is 5, then negative 3, that way. And remember, if I add the 2, I'm supposed to get, this one is maybe positive 1, and then the other one is negative 2. So that is my point C. So point C, I can say this one is simply 1, then negative 2. And then I go to the last one, which is OD, referencing it from the original, which is D added to the translation. And in this case, this becomes, maybe we have negative 5, then 3, then this one is added to, positive 5, and then this one is added to negative 3, and this one gives us 5, negative 5 plus 5, this one is a 0, and then 3 plus minus 3, this one is a 0. So our point D prime here will be at 0, 0. Our C prime, we have said, is at point 1, negative 2. Our B prime is at negative 3. And that is now what you can come and plot on our Cartesian plane with point D there. Then the others, of course, follows. So we go to the next. And in this, we have the collinearity. And we say that a point A, B, and C are collinear if they lie on the same straight line. And how do you tell that a point lies on the same straight line? We know that point on a straight line share the same gradient. Maybe we can have this example and consider their gradient. Maybe, for example, here I may consider point L and N, and also point M, point maybe M and N. So let us find the gradient of this. We know that gradient will always be given by change in y divided by change in x. So let us consider the first point, L, N. The gradient of that line, L, N, will be, so change in y, if I take the first term, change in will be negative, change in y will be negative 10 for L, then minus 11, that will be the gradient for that, minus 11, and then divided by the point of the other point, which is here we have x, the change in x, which is negative what, which is negative 2, then minus 5. So this gradient will give us what? So remember this was x and the 11. So we have negative 10 minus that. This one gives us negative 21 divided by negative 2 minus that. This one gives us negative 7. So negative and negative. So we are left there with the 3 positive. With the 3 because this and this cancels, and then the other one of course cancels to a positive. Then let us consider another point, which is point what? Which is point m n here, and then we can say that in this point we can have 11 then minus 2 divided by 5 minus 2, and in this case we can say that this one is 9 divided by 3, which of course gives us a positive 3. So you can see they have the same gradient. They have the same gradient, and if they have the same gradient, we can say that the lines are, these points are collinear. This point are collinear. So they are collinear because they have the same gradient, because maybe we can say that gradient mn is equals to gradient of ln. So that is one way you can give the collinearity. Now let us use the second method, which we can have them in vector form. So in this, we can say that the collinear and the parallel vectors, and we know that if two vectors are such that one is a scalar multiple of the other, then they are parallel. That is, if A and B are two vectors, A and A is equals to KB, where K is the scalar, we can then A and KB are parallel. And to verify that the vectors are collinear or not, we show that they are parallel, and then ensure that these ones are what? Ensure that they are, maybe for example, if I may have the point like this, if I may have the point like, maybe for example there I have this point, and then I have the last point here, it is moving in this direction, this is A, and then I can also have another point at the middle here, which is B, and then this I can have the point C. Then if A, C, is equivalent to K, which is the scalar, and then we have A, B, that way, then we can say that the point, maybe the point A, B, and C are collinear. So that is how we can tell. Maybe for example, let us do it in an application. We see how it works. So we are given that AB is that 4, 3, and then CD is that. Show that the point AB is parallel to that. So remember, for us to be able to say that they are parallel, we know that if they are parallel, that we know that point A, B, for it to be parallel, it must be equivalent to scalar multiplied by C D multiplied by CD. So, and in this case, we know that our AB, we are given it as 4, 3. Then here we can say that K multiplied by CD, we know it is the same as 2, then 1.5. That way. So now we can get the value of K by saying 4 is equals to 2K, and then we can divide by 2, so we get our K is equals to 2. The same case, we can use the other value, which is 3 is equivalent to K then 1.5. Then you can divide by 1.5 on the other side, 1.5, and also we get k is equals to 2. And also we get k is equals to 2. And then we can say that AB that way is equivalent to 2, maybe CD is equivalent to 2 CD, and that tells us also we can say that if these points are collinear, also we can also say that they are parallel. To express the parallel, we can say that AB is parallel to maybe CD. You can prove it by getting the gradient. You know that gradient of parallel line is also equal. Let us apply another example. And here we are told that by the use of vector, show that the point L, which is -2, -10, M, which is 2, -2, and that are collinear. We show that they are collinear. And for them to be collinear, remember they must be sharing the same point. So we can maybe take they share, we can take L, N, and then also we can reference L, M. Remember the point that they are sharing is L, the original point. So the common point there is maybe L, and then we can say that our Ln, this one will be equivalent to maybe K L M that way. So let us try to work it, we see. And we know for us to get Ln, if we reference that is Ln, this one is the same as N minus L. Of course, this one is given out by, if you press them LO, remember you Ln, you will have changed the direction. Remember, initial direction is supposed to start from OL. So that's why we are subtracting the head there. And then this one is maybe head N and then plus ON. ON, we are not changing the direction. That's why we are taking the N to be positive, referencing it using the original vectors. So with regard to this, we can take the point of N, which is 5, 11. Then this point we subtract the point of L, which is -2, then -10 that way. And then if you subtract those points, you are supposed to get this one being. So we are going to have this point being what? Ln. So we are going to have it being, here we are going to have it being 7, because of 5 minus -2, which is a positive, and then 11 minus -10, which is a 21. That way, 21. And then we can get the Lm also. Remember Lm, we can use the point of Ln, which is 2, and then this one we subtract the point of N, which is also -2, -10, and this one will give us a 4, because of 2 minus -2, a minus followed by a minus give us positive. Then we have 2, then minus -10, which gives us a positive 12. That way. So now it is obvious for us to say that 7 and 21, this one is equivalent to K, then this one multiplied by 4, 12, 412, multiplied by 412. And for us now, we can use one of them. We say that maybe, for example, if you take the first one, we can say that 7 is equivalent to 4K. Then we can divide whole side by 4, so we can get the value of K is equals to 7 is equals to 7 all over 4. Then the second one that we can have, we can also use the other one, which is the 12. We say that 12k is equals to 21. Then we can divide by 12. We divide by 12, and here we get the same k is equivalent to 7 out of 4, because if we divide by 3, of course we get that. And now it is obvious for us to say that Ln is collinear to 7 divided by 4 Lm, that way. And also we can say that our Ln is also parallel to Lm, if that was because this one cannot be parallel because they are in the same what? Because they are in the same line. They are in the same line. So we go to the next, we proceed to the next question. And here we are given point, the point of that, given the point P, 1, 3, -2, and the Q is that, show that they are collinear. You show that they are collinear. So we can reference the point. We have maybe PQ, and PQ, we can say that PQ will be given by, we subtract the Q, which is 2, maybe 1, 1, and then we subtract the P, which is 1, then a -3, and then -2, and then when we subtract these, we are supposed to get 2 minus 1 is 1, so this is 1, and then -2 because of so we are going to have remember this was 3, so we are going to have 1 minus that is -2 there, -2, and then the last one is going to be a positive 3. So now our PQ is the same as 1, then -2, and then 3. That is our line PQ. So now still we can get the line QR, the vector QR, and in this case we can subtract the point of R, and we know that R is 6, -7, and then 13. So these we subtract 8 from, maybe we have the Q, sorry, we have the Q, which is 2, and then we have 1, 1 that way, and then this one should give us the value as, maybe we have the first one, which is 6 minus 2, which is 4, and then the second one, which is -7 minus 2, which is -8, and then we have the other one, which is 13 minus 1, which is 12, that way. That is how we can get that. So in this case now, if we factor out 4 out of this, we will get 4, and then here inside we shall remain with 1, and then -2, and then 3. And you can see this is equivalent to PQ. It is equivalent to this PQ. So it is true for me to say that QL is the same as 4 PQ. And since 4 is the scalar multiple, we can say that they are collinear. That is, this P maybe is collinear. And then we are told to determine the ratio in which it divides. Maybe, for example, I had a point like this. This was my P, this was my Q, and then this was my R. And then there was a reference point here which was 0 ohm. If I connect all this up to here, So we are supposed to see how this line was divided to this, and then we can say PQ, this one is equivalent to what? 1:4. So you can say that the ratio of maybe PQ is to maybe QL, this one is equivalent to maybe 1:4. So the ratio was 1:4. And thus bring us to the end of this session. I was your trainer, Maurice Morene. If you found this video of importance to you, please consider subscribing, like, and share it so that it can reach more people. Thank you.